I have a chance, we'll do one up for homework to review binomial. I was going to do that as a warm-up, but I want to make sure I do a good job with the lesson, so here we go. Okay, so this is another series problem, and this is, actually everything is series from now on. Sets 144 through 148 are all series. This is for the case when it's a non-alternating series. How do you do an error bound if it's not alternating? Well, it's this a little more liberal error bound, kind of expand, it's a wider region, but it's still useful, all right? So just by way of review, if we used only 4 terms to estimate this series that is alternating, then we would typically call that S4, yeah? By leaving off so many terms, in fact, infinitely many terms, there is error. Now, we have been calling this error, but some books call it the remainder. Kind of like when you use long division, right? You sometimes get a remainder term. Now, we know that for alternating, all that error is less than or equal to just the next single term, A5. We're leaving off infinitely many terms, but all that error aggregated has to be less than A5. Now, if you think about the alternating nature of this, that makes sense. After A5, it starts to decrease, increase. And so it makes sense that A5 would be greater than all this stuff inclusive, because A5 is reduced after that a little bit. And so A5 is greater than all that stuff. You with me so far? All right. Now, I don't think I want to say anything to me. I think I said that. Some books call it remainder E, some call it R. Now, if it's not alternating, that's the topic of the day. What do? Well, if we use 4 terms, we're definitely still going to call it S4, no change there. But we could still look at this as the error or the remainder in using 4 terms only. Okay? But I think you can agree now that because these are all positive, A5 and all these is not less than just A5. All that error is A5 and a lot more, or a lot of terms more, right? So here, the error is not less than just A5, the next term. And yet, because this is a converging sequence, if these terms go to 0, and there even has a chance, then these are going to be pretty small. And so if you just gave this guy a little bit of help to get it over the hump of leaving all those other positive terms off, you can actually use the next term for an error bound. Now, that's the ideal Lagrange. The proof of this is pretty rigorous, and I'm not going to do it. Just the using it is enough. But the idea for Lagrange is if you give the next term a little more power, then you could use it for an error bound. Now, here's what I mean by giving it a little more power. Rather than the normal error bound being the next term, which is the next derivative at c, x minus c to the n plus 1 over n plus 1 factorial. Isn't that what normally we'd use for the next term as the error bound, right? That's how we find the next term. You with me? Okay. Now, this is where we give it a little more oomph. Rather than finding the rate of change or the derivative specifically at c, we're going to give it a little more help by using this m idea. This will look a little like trapezoid error bound here. The remainder, which is the difference between the true function and the Taylor series, is kind of like the next term, but I'm going to call it a super next term. Now, let's be clear. That is my terminology. Do not say that in college. They'll think you're an idiot. There's no such thing as a super next term in a textbook. You're never going to see that. But that's what helps me remember it. M is to give this next term a little more help to account for all those little terms that got left off. The little help you give it is M is the max or upper bound. It's kind of like the greatest possible value on the next derivative without respect to sign. So it's the max or an upper bound for the absolute value of the next derivative on the interval from where you're estimating to where you're centering. Now, I know right now you're probably thinking, I don't get it, I don't really know what you're talking about. Once you see a problem, you'll see it's not a big deal. It's not too changed from alternating series error bound. The bound will be a numerical value. When you say the error bound, you find a number. It's not some kind of x minus n expression. It's numerical, right? Would you write in here that for sine and cosine, you often use the fact that sine and cosine are both less than or equal to 1 in finding m. That'll make sense in a second. And for e, we often use the fact that e is less than 3 is pretty common in textbooks. We know e is about 2.71, blah, blah, blah. We'll use 3 as a standard. All right, now, let me show you what a problem looks like. Is this on the back? I understand the notes are slightly different here. Don't worry about it. I know I diverged a little bit. There was a little piece of that in plus 1. You'll be good. Okay, now, you see where I'm at there. This you should be able to do part A. Would you do part A for me, just as a good review that you've been keeping up, and you can write a Taylor series around a given center. If you can't do part A, you really should come in and get some help, because that's something at this point I would expect you to be able to do. Do you agree with the Taylor I have so far? Okay. Is that it for part A? Is there a little more? Yeah, the idea is now you use that to estimate the sine of 1. Sine of 1 then could be approximated by T3 at 1. And so that would be root 2 over 2 plus root 2 over 2, 1 minus pi over 4 over 1 factorial. Minus root 2 over 2, 1 minus pi over 4 squared over 2 factorial minus root 2 over 2, 1 minus pi over 4 cubed over 3 factorial. Okay, that's my approximation, and that's part A. Are we good? We could put that in our calculator, obviously, but we could. Questions so far? Are you doing well there? Were you able to do that on your own? Okay. Part B then, Lagrange error bound. First of all, why Lagrange? Lagrange because it's not alternating. Okay? If it's alternating, use alternating because it's a superior error bound. It is a smaller window of the error than Lagrange's. Lagrange, because of its max possible, is usually a little bit larger than the alternating usually would be. Okay? So we're going to use Lagrange because it's not alternating. The difference between sine of 1 and our Taylor, whatever that big thing equals, is less than or equal to superterm. Now, I tend to write this the first few days just because the more I write something, the more I remember. So I'm going to write the generic formula and then plug in a little bit at a time. I'm going to leave M for the last. For this estimate, what is x minus c each time? 1 minus pi over 4. You can see why the absolute value needs to be there because that would be negative. And we're not going to have absolute value over here less than any negative over here. That's ridiculous. Okay, so it's got to be there. N plus 1. Now, n represents the degree of the Taylor I use. So I used the third degree Taylor, so n plus 1 is the fourth. I left off at third, so the next term is the fourth. So far, it's just like alternating series error, right? All right, so m then. M is the max or an upper bound, a logically chosen upper bound for the absolute value of the fourth derivative on the interval x to c. Now the interval x to, I'm going to say that slower, x to c is what? What's x, what's c? 1, 2, pi over 4. Is that the right way or should I switch that? Which one's smaller? Pi over 4 is actually about 0.75, right? So I'm going to go pi over 4 to 1, yeah? Are you down? Okay, what is F for? This is where you might not have charted the derivatives, see, but I'm smart. I charted the derivatives. F3 was negative cosine, so F4 is sine, excuse me. The max of sine on pi over 4 to 1. Now, here's where it helps to think of a picture here. A sinusoid looks like this. Oops, that's terrible. Okay, here's pi over 2. Here's pi over 4. Where's one line? In between, right? Okay. So here's 1, and here's somewhere. And so, where will the max be? At pi over 4, 1, or somewhere in between? 1, okay? So here's where we distinguish between max or logically chosen upper bound. Technically, the max on the interval is sine of 1. So why not use sine of 1? That's the question. I don't know the sine of 1. That's the whole thing I'm trying to do. You don't bound something with itself. Okay, that's at least with most, except, and there's at least one textbook that uses sine of 1, but most textbooks say that's ridiculous. We don't know that, but I do know that no matter what sine of 1 is, it definitely is less than or equal to 1. See what I'm saying? Now, pause for a second and think, what if I had asked you to estimate sine of a half, okay? Sine of a half, well, that would be the interval from 1/2 to pi over 4, and 1/2 would be over here. Now, if the question had been the max of sine on 1/2 to pi over 4, then what's greatest, sine of a half or sine of pi over 4? Pi over 4. In that case, then it would be logical to choose an m of sine of pi over 4 or root 2 over 2, and you could use that for your m. Although you could still use an m of 1, and that's some people just, anytime they see sine or cosine, they just say 1, okay? You have choices, and both will be, there would never be an issue on the AP test where 1 is right and 1 is wrong. Do you understand what I'm saying so far? Okay, so the max then is going to be 1. 1 minus pi over 4 to the 4th over 4 factorial. So the error is no less than, or no more than, excuse me, the error or the remainder is no more than that, which is pretty doggone small. I mean, 1 minus pi over 4 is about a fourth to the fourth over 24. That's pretty close. Do you see what I'm doing so far? You good? You are a dead bunch. All right. It's kind of hot in here. Maybe that's what it is. I should keep it real cold like an operating room here. Keep it. Yes.
Why can't you just make the m sine of 1?
Because, so what's the question in this problem?
Find the error out.
Well, no, question is,
Oh,
estimate the sine of 1.
yeah.
So, I mean, that's why. I don't know what the sine of 1 is. That's what I'm doing.
Oh, okay.
Yeah, so it's because, in this case, sine of 1 is unknown, so I couldn't use it to bound itself because that's what we don't know. You see what I mean? If it had been sine of something unknown, then I would have used it. Okay? All right, so let's go here. Would you do part A again, please, on your own, and then we'll talk through and see. Well, it's not usually, it's usually junior high kids. This, I feel like, it works, but I'm afraid some of your stuff is too. Well, here. Well, it worked fine. I had it fine. And some junior high kids said, ooh, let's screw it. And then nothing. And then that one, they just broke the head off of it altogether. Actually, they're pretty good, actually. I don't like the junior high kids most of them.
So is the period the worst?
You guys are pretty good. I gotta say, good period at least brings a little energy. This one you shouldn't have to do the derivatives because this is, to me, a memorized fact. Are you starting to get your big 4 memorized? Okay. Are we all at the same place on A? Our estimate would be 1 plus 2 plus 2. Then we start to get towards e to the second, which I imagine is 2.7 to the second, below 9. And imagine we'd start to level off and get closer and closer to what it was. So far, so good, part A? All right, B then. Here we go. Lagrange error band. How much error? First of all, why Lagrange? It's not alternating. All right, so we're going to use this idea that the true value of e squared and our estimate, which I didn't total, but I could have a number there if I had totaled that, is less than or equal to super term. The next super term is m x minus c to the n plus 1 over n plus 1 factorial, and then let's nibble away at that. I'll leave m again. What's x minus c here? X is what we're estimating, so in this case, 2, and c is the center of the polynomial, and that's 0. What is n plus 1? 4. We left off at 3, so n plus 1 represents the next, which is 4 over 4 factorial. And then let's talk m. M is, what does it stand for? Is upper bound for the fourth derivative. Yeah, the fourth derivative on the interval from where to where? 0 to 2. Okay. Thankfully, E is pretty great because we can definitely, and that should be, this doesn't matter in this case, but I'll throw it on there just for you. What is the fourth derivative here? e to the x on 0 to 2. Would this be at its greatest at the left at 0, the right at 2, or somewhere in between? Right at 2. So the max is e squared. But this again is one of those cases where I don't know e squared. That's what I was trying to estimate. So instead of using a max, we're going to use a logically chosen error bound. For e, it's pretty common to say that e is less than 3, so e squared is less than 3 squared. So we're going to let m equal 9. You see where I'm coming from? So the error, or the remainder, you'll see both, is less than 9 times 2 to the 4th, or 16 over 4 factorial. So that's a little bigger error, max error. What do you reckon it is? The last one was so small, sine of 1. Why is this error so much? What? The center is pretty far from 2. That's definitely one reason. What else? What about the nature of the function? You're not talking sine, which deals with small numbers. You're talking exponential growth. And so it stands to reason your error will be greater when you're talking exponential growth. Okay? And you're right. The center is far. What you do? Try. Oh, what? Oh, shucks. I didn't even do that in the last class. And you know what they said? Nothing. They just let it go. Yeah, you're better. I didn't hear you say anything actually. I hear Claire saying how many terms necessary to get error less than 1? So if the error is to be less than 1, first thing is many people will mistake where that 1 goes. It's not the error is 1, so it goes here. The error needs to be less than 1. Well, the error then, it's a kind of a trichotomy. The error is, I know, less than the next term, and if that in turn is less than 1, then the error will be less than 1. So in terms of where that 1 goes, it's to the far right. The error is less than the error bound, and if the error bound is less than 1, I'm not going to roll in my error is less than 1. Okay? Now then, I dump the error part of it, and I say here, what is m still? 9. X minus c, that's still there. I know that. That's still 2 minus 0. But the question is, what is the n plus 1 factorial? And n plus 1 such that this is less than 1, yeah? You see where I'm coming from? Yeah. Okay, so unfortunately there's not a lot of algebra to be done here. 9 times 2 to the n plus 1 over n plus 1 factorial needs to be less than 1. I guess we can move the 9 over. Do you want to do that? Or just keep it the way it is and start trial and erroring. All right, so when n equals, how much was our error there? It was about 16 over 24. The error here was about 6, I would say, ballpark. So we're going to need well beyond that, okay? So I would start with maybe trying 7. What about 9 times? Yeah, what's the number of terms versus the derivative? Is that what you're going to say?
I'm just like, since that one was n equals 3, wouldn't you try n equals 4 or 5?
We tried, yes. Oh, you feel like I'm jumping too far down the line?
Yeah.
We could try 4 or 5. What do I do? Oh, thanks. Where's that? Sorry, I don't have my glasses on.
That's a great task.
Thanks, Bob. You're really helpful. Excuse me. All right, so, oh, good point.
Thank you.
Oh, yeah, I think we're good.
That's excellent.
Yes, thank you for mentioning it. All right, Nathan, you got me. So let's be more systematic instead of jumping around. Is 9 times 2 to the 5th over 5 factorial something that's less than 1? Strangers in the world.
You get 12 fifths.
12 fifths? So that's not it.
I'm glad we have one.
Okay, how about n equal 5, which is 9 times 2 to the 6th over 6 factorial?
Or
8/10? Are you guessing or you just actually?
no, I did the math.
Oh.
6480.
There you go. Okay, so n equal 5 makes this come out to be less than 1, right? This is less than 1 when n equal 5. Here's the part that kicks my butt. So I would, being a lazy guy, I would then usually say, yep, 5 terms, boom. That's through n equal 5 in the Taylor formula. But does n start at 1 in the Taylor formula? It starts at 0. And so when you go through n equal 5, how many terms is that? That's 6 terms. Okay, so to answer the question, well, how many terms necessary? We would have to have 6 terms. Because n starts at 0, 6 terms. We would need n equals 0 through n equal 5, and that's 6 terms. Yes?
So when you do like finding the term number, since n has the max of like the fourth derivative, that just doesn't n just doesn't change even though you're changing the
Oh, oh boy. Oh man, you're right. Oh, you're right. Are you right? No, you're good. Okay, so the derivative in all orders, didn't even think of that. In many cases, that could change, you're right. I didn't even think about that. But in this case, do you agree that the derivative in all orders would still be e to the x? And it's still going to be 0 to 2. And so in this case, it is going to stay 9. But you're right to think about that because it could change. Good point. That's great. Okay. And then try this one on your own and all the way through, including the error bound. And you should be, if you can do this, then I will believe that you have a great start.
Is that one of the 4?
It is not, although, yeah, no, that's not. I would take derivatives if I were you. Many textbooks do have you memorize this one, and maybe we will eventually. But sorry, somebody distracting me. Kiss the flags off. Kiss somebody. That's enough.
No, keep it that way.
You want to make me new?
Yeah, you got it right here by me.
Run the
How
mile.
about if I turn it off?
No, turn it up all.
Happy compromise.
Ah,
Oh, sorry, I didn't think about that.
I didn't know.
That's my specialty. You okay, Yulia?
Okay.
Okay, phew. That was close.
It's so long.
So if we get to like,
Yeah. Don't worry about getting this on if you have the time and the inclination, you could get this in. In this case, they're just fractions. It's not a big deal. So you might be thinking at this stage in the game that you're thinking, gosh, it looks alternating to me. Oops. How we doing? Do you have part A somewhat like mine? Is that alternating or not? It's not. The first term is negative. Second term is, this is squared, but that's negative, so that's negative. Third term is a negative cubed, that's negative. It's negative, which for log of a half makes sense. Yeah? So it's not alternating, that's why Lagrange. Continue on to part B if you have that much time.
is that supposed to select alter here? So I'm getting 96.
No, it should be less than 1. 96, is that M or is that?
It's the fourth derivative at 1/2. 6 over x, the fourth at 1/2.
Negative 6 over, so what are you using, which would give the biggest number, when x is a half or when x is 1?
Negative 6 versus negative 96. Negative. But negative 6. Oh, okay.
I'm not sure.
Okay, yeah. Negative 6 is better.
It seems like every one of these is through the third degree. That obviously is not always the case.
Okay, so we're just
Okay.
is analog a negative term?
No, that's why the absolute value. So M is the max of the absolute value of F4. Sometimes they'll give you a graph on the AP test, and you have to interpret the graph for the next. On the interval from 1/2 to 1. Now, F4 is negative 6 over x to the 4th. The absolute value of F4 then is 6 over x to the 4th. The max of that on, did I make a mistake? Oh, Max of that, I'm gonna have to 1. When will that be at its greatest? When x is at its greatest or when x is at its least? When x is at its least, you get the biggest outcome. So that's 6 over a half to the 4th, which is 96. So you're right to say that m is 96. The error bound, though, is 96 times 1/16 over 24. 24 goes into 96 4 times. 4/16 then is 1/4, and won't you agree that that is less than 1/2? The error can be proven to be no more than 1/4, and therefore it is also less than 1/2. Do you agree? Do you agree? Okay, that is that. What do you want to go over questions on? I put the keys to 142, 143, and the extra practice. Just hints and answers on 143. What do you want to go over first?
I thought we were doing a little binomial this problem.
Oh, do you want to do a binomial warm-up on tonight's homework?
Yeah.
Or do you want to do questions on 143 extra practice? All right. On tonight's homework, go to box. Tonight's homework's at 144. Let's have you give. It's not working out so well. How about 6? No, 8. Do you have an 8, number 8 box?
Yeah.
Okay. Box 8 on tonight's homework on set 144 is estimate the cube root of 1.625 with error less than 100. So I would start with,
Are the other shits still going to be?
say it again?
Are the other shits still going to be? We don't ask questions.
No, I'll take it easy this week. Well, preferably by Wednesday. Let's go by Wednesday. Okay. So I'm kind of curious, when you go to do the binomial series for this, would you think derivatives and just kind of mentally do it, or would you think summation notation? Wow.
Repeat the question.
How would you, what's the requirement for this?
Isn't it just p minus 1, p minus 2 times, or
What the heck is that?
isn't it 1 plus x to the p?
1 plus x to the p, yes, is 1 plus, let's review this. Okay, I guess we need to review. 1 plus x to any power is 1 plus p, x to the first over 1 factor, plus p times p minus 1 for the next power that came down, x squared over 2 factorial, and so on. So what is 1 plus x to the 1/3? All right. So how's that going?
What is your series then?
This summation notation is just to remind you it's final. You don't need it there. It didn't say right the general term, but the general term is p choose n x to the n.
Are we allowed to use physics on this?
Sure. Yes, you'll need a calculator. So now you get into what you're trying to estimate. What is the fraction form of 0.625 if you're so inclined? 5/8. So whatever, fraction or decimal, whichever your heart desires. Remember, you want to store as you go. You're doing two things. You're trying to find where it starts to alternate, and you're trying to find a sum after that. So store as you go. As you find each individual term, store it. Store that to A, store that to B. Keep going until you find an error bound. This is alternating. So you can use alternating error bound. Did you get the third term was about 400s? Negative. I got third term was negative 0.043. Did I make a mistake? What? Oh, okay. The fourth term I get,
Oh, he does.
the fourth term I get 0.015, which is just a little too big.
Yeah, I'm in it again. I got that.
Okay.
Nathan, I'm the next person to do that.
Alright, and then sorry, what I lost my I made a mistake typing. What about term 5? Yes? Do, do, do's. So slow. Okay, so term 5 is 6 thousandths roughly. Alright, so let's do this then. Let's get our estimate. The cube root of 1.625 can be approximated by some, what did I say, some 4? And so what is the sum of the first 4? 1 plus 3 plus I'm getting a sum of 1.9503-ish. Do you agree?
Yes.
This is an, so let's talk the justification for saying why this is exactly not. This is an alternating series. If the term's going to 0 and decreasing. So it must be the case that the error between the true infinite sum, which you could call S, or you could just say the cube root of 1.625, and our estimate, which is S4, is less than or equal to A5, which is roughly 0.006, and that is less than 0.00 or 0.01. And therefore our error is less than. Cool? All right, got that one done at the very least. That's a little harder work. Okay, people. Well, seniors, have a great day. You lucky dogs. Juniors, juniors. I didn't make any old beginner level math reviews. Are you guys keeping up? Do you know how to add numbers and do algebra and geometry? You don't care? All right. You're just going to show up and be here. I will, if you're done with anything, turn it in. If you need more time to work on it, fine. Yeah, it kind of depends on if you need the keys from them.
Sorry for being
Oh, dude.
That's fine.
The keys are online if you need an extra day to look at them. If they don't make sense, ask. I thought you guys all knew. I don't know. Are they going to call you down? Brady, do you know?
Yeah, it's like classic is and senior grade, so it's
They'll probably do a scare you